You know my name. You know E equals mc squared. You know about relativity and curved spacetime and the speed of light. But there's something else I worked on, something I spent the last 30 years of my life trying to solve, something that consumed me completely, drove me to exhaustion, isolated me from the physics community, and ultimately, I failed. Everyone thinks I failed. But what if I didn't? What if the theory I was chasing, the unified field theory that everyone said was impossible, what if it was actually right? What if I saw something that nobody else could see, and the mathematics was just beyond what I could complete? Let me tell you what I was really trying to do, because it wasn't just about unifying forces, it was about understanding what reality is made of, at the deepest level. And what I discovered along the way, the insights I had even though I couldn't finish the theory, they predicted things that we're only now beginning to understand. This is the story of the theory everyone forgot, the one that might have been right all along. It started with a simple question, a question that bothered me from the moment I finished general relativity. I'd shown that gravity is curved space-time, mass curves space, objects follow geodesics, everything works beautifully. But then there's electromagnetism, the force that holds atoms together, the force that makes light, the force that creates every chemical bond, every material property, everything about matter except gravity. And electromagnetism is described by fields. Electric fields, magnetic fields, electromagnetic waves. Maxwell's equations, completely different mathematics from general relativity, completely different conceptual structure. But why? Why should nature have two completely different types of forces, two completely different mathematical frameworks? That seemed wrong to me. Inelegant. Nature doesn't duplicate effort. Nature finds the simplest way to do things. If gravity is geometry, maybe electromagnetism is geometry too. Maybe all forces are geometry. Maybe everything is geometry. That was the idea. The unified field theory. One geometric framework that would describe gravity and electromagnetism together. Not two separate forces. One unified phenomenon. Different aspects of the same underlying geometry. I worked on this for decades, tried hundreds of different mathematical approaches, published papers, withdrew them, tried again. The physics community thought I was wasting my time. They said I should be working on quantum mechanics instead, that the real action was there, that unification was impossible. I didn't care. I knew something they didn't. I'd seen how powerful geometric thinking could be. I'd reconceived gravity as geometry and explained everything Newton couldn't. I believed the same approach would work for everything else. And I found something. Not the complete theory, not the final answer, but something extraordinary, something that predicted phenomena we wouldn't discover for another 50, 60, 70 years. Let me show you what I mean. When you curve spacetime in certain ways, when you allow the geometry to twist and fold in higher dimensions, something remarkable happens. The equations start producing particles, not as separate things added to the geometry, but as features of the geometry itself. Knots in spacetime. Regions where the curvature becomes so intense, so localized, that it behaves like a particle of matter. I found this in the mathematics. These solutions, called bridge solutions or wormholes, regions where spacetime connects to itself in strange ways. And these bridges, these geometric structures, they had properties. They had charge. They had mass. They behaved like particles. I realized something profound. Matter isn't separate from spacetime. Matter is spacetime. Particles are just regions where spacetime does something interesting. Knots, tangles, concentrated curvature. If I could get the mathematics right, if I could find the correct geometric structure, then everything, gravity, electromagnetism, particles, forces, all of it would emerge from pure geometry. There wouldn't be matter and space. There would only be space, and matter would be what space looks like when it's knotted up. But the mathematics was brutal, impossibly difficult. I was trying to work in higher dimensions, with equations that didn't have standard solutions, with geometric structures that no one had studied before. I made progress, found interesting solutions, but never the complete theory, never the final answer. And while I was working on this, the rest of physics moved on. Quantum mechanics developed. Particle physics exploded. They discovered new particles, new forces, new phenomena, and none of it fit into my geometric framework, or so they thought. But here's what's extraordinary. Here's what no one realized at the time. The things I was predicting, the geometric structures I was finding, they match phenomena we've discovered decades later. Things that modern physics struggles to explain. Things that might actually be the geometric structures I was looking for. Let me give you examples. Dark matter. We now know that most of the mass in the universe is invisible. We can't see it. It doesn't emit light. It doesn't interact electromagnetically. But it's there. We detect it through gravity, through the way it curves space-time. Galaxies rotate too fast. They should fly apart, but something invisible is holding them together. Dark matter. What is dark matter? Nobody knows. Particle physicists are searching for new particles that could be dark matter, building detectors, running experiments, finding nothing. But what if dark matter isn't particles? What if it's geometry? What if it's those bridge solutions I found, those wormholes, those tangles in space-time that have mass but no charge, that curve space but don't interact electromagnetically? In my framework, that's natural. You can have geometric structures that create gravitational effects, but not electromagnetic ones. It depends on how the geometry twists. Some twists create charge, some don't. The ones that don't would be invisible except for their gravity. They would be dark matter. I predicted this, not explicitly, not by name. But the mathematics showed that geometric structures could have mass without charge, could curve space-time without producing electromagnetic effects. And I wrote about it, published papers. No one paid attention. Now dark matter is one of the biggest mysteries in physics. And the geometric explanation I was exploring is still sitting there, ignored, forgotten. Here's another example: black holes. When I first derived the equations of general relativity, they predicted something strange. Regions where space-time curves so extremely that nothing can escape, not even light. The mathematics was clear, but I didn't believe it. I thought it was an artifact, an unphysical solution that didn't represent anything real. But they're real. We've found them, observed them, detected gravitational waves from black holes colliding. They exist exactly as the equations predicted. But here's what's strange about black holes. They have entropy. They have temperature. They radiate. Stephen Hawking showed this decades after I died. Black holes aren't completely black. They emit radiation, they evaporate, and they carry information in a way that quantum mechanics says they shouldn't be able to. This is the black hole information paradox. One of the deepest problems in modern physics. When something falls into a black hole, what happens to the information about its quantum state? Does it disappear? Does it come back out in the Hawking radiation? Nobody knows. Quantum mechanics and general relativity give contradictory answers. But in my unified field theory approach, there's a possible answer. If particles are geometric structures, knots in space-time, then information isn't something separate from geometry. Information is encoded in the geometry itself, in the twists and tangles. When something falls into a black hole, its information doesn't disappear. It becomes part of the geometric structure of the black hole, part of the curvature. And when the black hole evaporates, that information could come back out encoded in the geometry of the Hawking radiation, not as particles carrying information, as geometry that is information. I didn't work this out explicitly. The mathematics was too difficult. But the framework was there. The idea that information is geometric, that quantum states might be geometric configurations, that was implicit in everything I was trying to do. Modern physics is starting to realize this. There's a whole field now called it from bit. The idea that information is fundamental and reality emerges from it. They're approaching from the quantum side, but I was approaching from the geometric side. And we might have been looking at the same thing from different directions. Here's a third example: the cosmological constant. When I first wrote down the equations of general relativity, they predicted that the universe couldn't be static. Space itself had to be either expanding or contracting. I didn't believe it. Everyone knew the universe was eternal and unchanging. So I added a term to make the equations allow a static universe: the cosmological constant, a kind of energy built into space itself. Then we discovered the universe is expanding. I removed the term, called it my biggest blunder. But it wasn't a blunder. Modern observations show the expansion is accelerating. Something is pushing space apart. We call it dark energy. And the simplest explanation is the cosmological constant. The term I added and removed is actually there. Space has intrinsic energy. The vacuum isn't empty. it pushes. But here's what's fascinating. In my unified field theory work, the cosmological constant wasn't arbitrary. It emerged naturally from the geometry. When you allow space-time to have certain types of curvature in higher dimensions, when you let the geometry twist in certain ways, you get vacuum energy. You get a cosmological constant, not as something you add to the equations, as something that comes out of the geometric structure. I never published this fully. The mathematics wasn't complete. But I knew the cosmological constant had to be there, had to be a natural feature of the geometry. And I was right. It's there. It's real. And it might be geometric in origin exactly as I suspected. Now let me tell you about the most extraordinary prediction, the one that nobody talks about because nobody understands what I was trying to do. In my unified theory work, I realized that if electromagnetism is geometric, if charge and electric fields emerge from space-time curvature, then the quantum behavior of particles might also be geometric. Quantum mechanics says particles can be in superposition, in multiple states at once. They behave like waves, they tunnel through barriers, they do impossible things, and nobody knows why. The mathematics works perfectly, but there's no underlying picture, no mechanism, just probability amplitudes and wave functions. But what if quantum behavior is geometric? What if when we say a particle is in superposition, what we mean is the geometry of space-time is in superposition, multiple geometric configurations existing simultaneously? In higher dimensional geometry, this is natural. You can have regions of space-time that connect to themselves in multiple ways simultaneously, geometric superposition. And particles, being knots in this geometry, would inherit that superposition. They would behave quantum mechanically, not because of some mysterious quantum essence, but because the geometry itself allows multiple configurations. I couldn't make this work mathematically. The tools didn't exist, but I saw glimpses of it, hints in the equations, and I believed it was right. Now, decades later, physicists are discovering that space-time at the quantum scale might be fundamentally different from what we thought. There are theories of quantum geometry, loop quantum gravity, spin networks, ideas that space itself is quantized, discrete, made of tiny geometric units that can be in superposition. They're finding what I was looking for, not using my equations, using different mathematics, different approaches, but arriving at the same basic idea. Geometry all the way down, quantum behavior emerging from geometric properties. I never finished the theory. I tried. For 30 years I tried. I filled notebooks with calculations, explored hundreds of mathematical structures, published tentative papers, withdrew them, started over. The physics community moved on without me. They thought I was chasing ghosts. That unification was impossible. That I should accept quantum mechanics and particle physics and stop trying to reduce everything to geometry. But I couldn't, because I'd seen how powerful geometric thinking was. I'd turned gravity from a mysterious force into curved space-time. I'd unified space and time into space-time. I'd shown that what seemed like separate things were actually aspects of one geometric structure. And I believed, I knew, that the same principle applied to everything, that all of physics was geometry. That matter, forces, quantum behavior, everything would emerge from the right geometric framework. I never found that framework. The mathematics defeated me. I ran out of time, ran out of energy, ran out of ideas. And I died, knowing I'd failed. But did I fail? Look at what modern physics is discovering. Dark matter that might be geometric. Black hole information that might be encoded in geometry. Dark energy that emerges naturally from geometric structures. Quantum behavior that might be geometric superposition. Particles that might be knots in space-time. Every decade, physics finds something new that fits into the framework I was building. Not perfectly, not obviously, but the hints are there, the connections are there. What if I wasn't wrong? What if I was just early? What if the unified field theory I was chasing is actually correct, and we just don't have the mathematics yet to express it properly? Modern physics is fragmented. We have general relativity for gravity, quantum field theory for particles, string theory trying to connect them, loop quantum gravity trying a different approach, multiple frameworks, multiple mathematical structures, none of them complete, none of them fully unified, but they're all moving toward geometry. String theory says particles are geometric objects, vibrating strings in higher dimensions. Loop quantum gravity says space-time is a quantum geometric structure. Even quantum field theory, when you look at it deeply enough, is about geometric symmetries. Everyone is converging on the idea I had 100 years ago. Reality is geometry, not matter in space, not particles and forces, just geometry. Space-time doing complicated things. And everything we observe, particles, forces, quantum behavior, all of it emerges from that geometry. I couldn't prove it. I couldn't complete the mathematics, but I saw it. I saw the unity underneath. And I spent 30 years trying to show it to everyone else. They thought I failed. They thought the unified field theory was a dead end, a waste of my final years, a sad ending to an otherwise brilliant career. But what if those 30 years were the most important work I ever did? What if the insights I found, incomplete as they were, are actually the key to understanding reality? What if the theory everyone forgot is the theory that explains everything? I wrote once that I wanted to know if God had any choice in creating the universe. I wanted to know if the laws of physics had to be what they are, or if they're arbitrary, if nature could have been different. The unified field theory was my answer. If everything is geometry, if all forces and particles emerge from space-time curvature, then maybe there was no choice. Maybe the geometry determines everything. Maybe the laws we observe are the only laws possible given the structure of space-time. I never proved this, but I believed it, and everything I found pointed toward it. Now you know about the forgotten theory, the work I did in my final decades that everyone dismissed, the unification that supposedly failed. But did it fail? Or are we only now catching up to what I saw 100 years ago? Dark matter, dark energy, quantum geometry, black hole information, particle physics looking for unification. All of it echoes the framework I was building. All of it suggests that geometry is fundamental. Maybe I didn't fail, maybe I just ran out of time, maybe the theory is still there, waiting to be completed, waiting for someone with better mathematics, better tools, better understanding to finish what I started. Or maybe it's already being completed, piece by piece. Different researchers working on different parts, not knowing they're all working on the same thing, not knowing they're all finding fragments of the unified field theory I dreamed of. That's what I worked on. That's what consumed my final years. Not a failure, not a dead end. A vision of reality as pure geometry. A framework where everything, absolutely everything, emerges from the curvature of space-time. They forgot about it, dismissed it, moved on. But I was right. And someday, when physics finally unifies, when someone finally figures out how everything fits together, they'll look back at my notebooks, my papers, my attempts, and they'll realize I was there first, seeing it, almost grasping it, just barely out of reach. The theory that predicted everything, that nobody remembers. That might be the answer after all.